Welcome back, class. It's Dr. Lindner. We are still on chemistry, and what we're going to be looking at now is chemical bonds. And chemical bonds occur when atoms are held together by forces of attraction. I think we spoke about attraction before with positives and negatives, right? The the number of electrons in the valence shell determines the likelihood that an atom will form a chemical bond with another. So the number of electrons in the valence shell are going to determine whether something is stable, whether it's unstable. Now, if something's stable, it's good by itself. If something is unstable, then we need to form a bond with something else. And I'm going to show you how that is. So here we're looking at carbon, and carbon has 6 protons, so it has 6 electrons. In the first valence shell, and this is called the first shell, and then as we move out, this would be the second shell. And if I needed to, I can make another shell that would be the third shell. The rule of thumb is that in the first shell, the maximum number of electrons, it can't go past 2. So you have 1, 2. So if we were to make carbon, if I was to do it with you, I'd say, okay, here's the nucleus, and I'm looking at an atomic number of 6. So I have to put 6 electrons. In the first shell, the maximum I can put is 2. So there's 1, 2. But I need to get to 6. So I need to add another ring. So I add another ring. There's 2, 3, 4, 5, 6. Now, I would say, is that stable or unstable? The outermost layer, in order for stability, needs to have at least 8 electrons. Since this doesn't, this is very unstable, and carbon has to form a bond with something else. And it will, and it does. So here are some common ions in the human body, and you should know these. These are probably going to show up. Some of these I would probably put on a test or an exam, but you should know that hydrogen is H plus, it's a proton. Sodium is Na for natrium. Potassium is the letter K. Magnesium, Mg. Calcium is Ca. Iron is Fe. Chloride is Cl. Notice this column has minuses and everything in this column has positives. When we look at the word cation, just remember cation think of the T, a lowercase t, looks like a positive. So all of these are cations. They all have a positive charge. These are all protons. The anions have 2 ends, so they're more negative. The ends for negative, there's 2 of them. All of these have negative charges. Okay. So chloride is Cl. I would know HCO3 is bicarbonate. I would know phosphate is PO4. Those are some of the biggies that I would know. Again, cations with a T have the positive charge, anions with 2 N's. These all have negatives. So atoms, these are the smallest unit of matter. They retain all the properties of an element. And we know that atoms consist of 3 types of subatomic particles. Those are the protons, neutrons, and electrons. The P in proton, think positive. The electrons, think of electricity. If you touch it, that would kind of suck. That would be negative. You'll get electrocuted. So electrons are negative, and neutrons are neutral. The nucleus itself, the nucleus is made up of protons and neutrons combined. Okay. We know that electrons are going to hang out over here in the outside in what we call electron shells. This is the first electron shell. This is the second electron shell. And usually the outermost shell, they call the valence shell. So the most likely region of the electron cloud in which to find electrons orbiting the nucleus, the electron shell can hold only a limited number of electrons. And here's how you figure out how many electrons can be held in each electron layer. So the formula is 2n squared, whereas n would equal to the number of the shell that we are referring to. So if I'm referring to the first shell, number 1, I would say the formula is now 1 squared. So we do what's in the parentheses first. What's 1 squared? 1 times itself is 1. What's 2 times 1? 2. So you can only fit 2 electrons in that first shell. Let's look at the second, utilizing the same formula, 2n squared, again, n equal to the second electron shell. So now we're doing 2 squared. So what's 2 times itself? What's 2 times 2? 4. So now you're doing 2 times 4 equals 8. So we need at least 8 in the second shell for stability. If it has 7, it's no good. If it has 1, it's no good. If 8 is the magic number and it doesn't have it, it's not stable. If we have 3, if we're talking about a third layer, if we're adding a third shell to this, and we do the same thing, 2n squared, now we're doing 3 squared. What's 3 times 3 is 9. So now we're doing 2 times 9 is 18. So the third shell can hold 18 electrons. Okay. So when we look here again and we go hydrogen, hydrogen has an atomic number of 1. It means it's 1 proton. How many electrons does it have? 1. How many should there be in the first shell? Well, 2 times 1 squared. 1 times 1 is 1. 1 times 2 is 2. There should be 2 here, and there's only 1. So stable or unstable, definitely unstable. Helium has 2. That's good. No problem. Carbon, atomic number is 6. So we know that the first shell can hold a maximum of 2. And now we just count up to 6. So you got 2, 3, 4, 5, 6. But that only has 1, 2, 3, 4 in the outer shell. Unstable. So carbon's going to have to hook up with someone else for stability. Let's look at sodium. How many are in its outer shell? Well, there's only 1. How many in the first shell? 2. That's good. How many in the second shell? 1, 2, 3, 4, 5, 6, 7, 8. That's good because you can have 8 there. But in the outermost, there's either got to be 8 or what did we say in the slide before? 18. And how many are there? There's only 1. Very unstable. So sodium is going to have to hook up with a friend to create stability. It just so happens that its neighbor here, chlorine, that has an atomic number of 17. How many are in the first shell? 2. That's stable. There's supposed to be at least 8 in the second. We got 1, 2, 3, 4, 5, 6, 7, 8. That's good. So 8 plus 2 is 10. That means we got 7 here. 1, 2, 3, 4, 5, 6, 7. That's a total of 17 protons, 17 electrons. But how many are in the outer shell? There's only 7. Not stable. Sodium isn't stable. But if these two join forces, this one can donate an electron. It can lose an electron to here. And that's exactly what happens. This loses the electron. This gains an electron. And then you bring sodium chloride together. Since we lost this electron, sodium becomes more positive because it's losing an electron. So it's becoming more positive in relationship to having the electron. And since chlorine gained an electron, it becomes more negative. So NaCl is sodium chloride, that's salt. This is called ionization. Ionization is when there's a gaining-losing type of relationship. That's called ionizing or ionization. And I'm going to cover that again in a second. So bonds hold together the atoms and molecules and compounds. The atom with a full outer shell, it's going to have a full outer shell that's stable. If it's stable, it's very unlikely that it's going to form a bond with something else because it doesn't need to. It's already stable. What makes it stable is that octet rule. It states that biologically important elements interact to produce chemically stable arrangements of 8 electrons in the valence shell, in that outermost shell. You want to have 8. Whether electrons are shared or lost or gained determines the type of bond that's formed. When it's losing or gaining, that's ionizing or ionization. And when it's sharing, we call that a covalent bond. A covalent bond is when there's a sharing. Ionization is when there's a losing and gaining type of relationship. So when an atom is unpaired, is an unpaired electron in its outermost shell. So if you have something that has 2 here, but you got 1 here and it's not paired, it's highly unstable, which means it's highly reactive. It's highly reactive. It can become stable. It can become stable if it gives up an electron, right? If it gives that up to something else, then you have 2 here, that's okay, and then something else can gain it, it's fine. Okay, let's look at oxygen. If we go back here, oxygen has 8 protons. So if we look at it, you got 1, 2, 3, 4, 5, 6, 7, 8. All right, is it stable or unstable? Well, you got 2 in the first shell. That's the way it's supposed to be. But we need 8 here. How many do we have? 1, 2, 3, 4, 5, 6. Not stable. So oxygen is going to form a bond with something else, and look what it does. Here, this is O2, because we have 2 oxygens, O2, right? You've heard of, like, if you have H2O, that's water, there's 2 hydrogens and 1 oxygen. In this case, we have O2. And if we look at it, how many do we have in the first ring? We have 1, 2. How many do we have in the outer ring? Well, we have to remember these come together. They're sharing here. Nothing's giving up. No one gave. No one lost. There's a sharing that's going on here. So let's count these. 1, 2, 3, 4, 5, 6, 7, 8. This appears to be stable. Let's count the other one. 1, 2, 3, 4, 5, 6, 7, 8. 8 in the outer ring appears to be stable, so oxygen is stable. Now, It becomes unstable if there's an unpaired electron. 1, 2, 3, 4, 5, 6, 7. Something damaged that other electron. This is called superoxide. It's very damaging. It creates damage to your DNA when we have this. Okay. So this free radicals are bad for us. It's bad for our health. It's produced in our body by the absorption of energy in UV light that comes in sunlight. X-rays, excessive amount of X-rays can cause damage by the breakdown of harmful substances and during certain metabolic reactions in the body. Fried foods give off free radicals. Smoking, drugs, medications, alcohol, even excessive exercise can create free radicals. Now, ROS and age, this is something that you're going to hear a lot about in healthcare. ROS stands for reactive oxygen species. A reactive oxygen species is like superoxide. It's very, very damaging. AGEs are advanced glycation end products. Advanced glycation end products. Glycation, the word glycation sounds like glucose. When you have an excessive amount of glucose that your body can't properly handle, it's just as damaging as superoxide or reactive oxygen species. So whether it's ROS or AGEs, they're very, very damaging to our body. This creates what we call oxidation. And when you oxidize the body in an advanced, accelerated way, it's no good. Think of what happens if you bite into an apple. If you bite into an apple, the white of the apple starts to bronze and turn brown because it's exposed to all that oxygen and it turns brown, it rusts. That's oxidation. But if I take a little capsule of vitamin C and I chop that up and I break it up into small little powder filaments, and if I break it up into this little powder, I bite into an apple and I take the powder of vitamin C, rub it on the white part of the apple, it won't oxidize because vitamin C is an antioxidant. So as long as we have antioxidants in our body, like vitamin C, vitamin E, selenium, beta carotene, these are antioxidants. So is glutathione. Glutathione is the most powerful antioxidants. Thione and thiols, these are kind of similar, powerful antioxidants. Glutathione we get from our diet when we eat protein. We need amino acids called glycine, glutamine, and cysteine. As long as you have protein, and in that protein we've got glycine, glutamine, and cysteine, our bodies can take these three things, bring them together, and make glutathione. If you're deficient in them, you have a difficult time in making it. It's a powerful antioxidant, and vitamin C is needed to help recycle it. So think of glutathione as like a bulletproof vest that's taking all the reactive oxygen species, all the advanced glycation end products, all the free radicals, and it's protecting us. It's taking all the hits, all the bullets, and then vitamin C comes along and helps recycle glutathione. That's amazing how that happens. But if you don't have enough antioxidants, then the oxidants win. And that's linked to a lot of diseases like cancer, diabetes, Alzheimer's, atherosclerosis, rheumatoid arthritis. So we can help to try and slow down the process by consuming foods rich in antioxidants. And those foods tend to be Roy G. Biv. right? Roy G. Biv are the colors of the spectrum: red, orange, yellow, green, blue, indigo, violet. When we say eat the rainbow, that's the rainbow. Red, orange, yellow, green. These are foods that have lots of antioxidants, the colorful foods. Eating the rainbow doesn't mean eating Skittles, folks. It means eating, fruits and vegetables, all of these different colors, loaded with antioxidants. Even people who receive spinal adjustments, they've done studies showing that patients who are under care for 2 years or more, for maintenance adjustments, have much higher levels of serum thiol in their blood. And serum thiol is a very important antioxidant that protects your chromosomes. They found that chiropractic patients who were receiving care for 2 years or more that had higher serum thiol levels had much longer telomeres. And a telomere is the protective cap to your chromosomes. The longer the telomere, the longer your cells live. The longer your cells live, the longer your tissues live. The longer your tissues live, the longer the organs live. The longer the organs live, the longer the systems live. The longer the systems live, the longer the organism lives. So the longer the telomere, the longer the lifespan. So it isn't just in nutrients and foods, but this was a huge study done about 10 to 15 years ago in my profession on wellness patients. So if you've ever wondered and asked, why are people healthier when they receive adjustments that have nothing to do with neck pain or back pain, but maybe they don't get as sick as frequently? Maybe their allergies aren't quite as bad. Maybe the child doesn't get as many ear infections as they used to. Maybe they don't get the same viruses or bacterial issues. It's primarily due to the adjustments increasing the serum thiol level, protecting your cells, tissue, protecting your chromosomes, basically. That's a pretty cool study. So now let's look at cations versus anions and ionic bonds. What we're looking at is sodium, and sodium has 11 protons, which means it's going to have 11 electrons, and chlorine should have 17 protons, which means we need 17 electrons. So let's kind of do the math. Let's kind of see if we can let's try and plug the electrons. Okay, let's do it from fresh. So if we have over here sodium, and let's say that's the nucleus of sodium with the protons and neutrons, and we say there's 11 protons, let's start plugging in the 11 electrons. So how many can fit in the first ring? It's going to be 2. Now we need 11. So I can't put 11 in this ring, so it forces me to add another electron shell. So let's count up to 11. We already got 2, 3, 4, 5, 6, 7, 8, 9, 10. I need one more. Can I just put 1 here? I can't, because there's already 1, 2, 3, 4, 5, 6. There's already 8 here. So I can't do that. So it forces me to add another shell purely for that 1 electron. Now we think of the octet rule. The octet rule says that the outer shell needs to have at least 8 electrons. Are there at least 8 in that outer shell? No chance, Lance. Nuh-uh, mama. No way, Jose. There isn't. There's only 1 there. So we're going to have to find a solution to this. It's going to have to join something. So it finds its friend, chlorine. Chlorine has 17. So let's put Cl here. We'll put the number 17, because that's what we're trying to get to, the 17 protons, the 17 electrons. How many can fit in the first shell? 2. How many can fit in the second? 8. So let's put 8 in. 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2 is 10. We need 17. So I got to add another one. We already got 10. So let's add 7 more. 10, 11, 12, 13, 14, 15, 16, 17. Unpaired. There's nothing here pairing with it. And does it meet the octet rule? Octet rule tells us there needs to be at least 8 in the outer shell. There's only 1, 2, 3, 4, 5, 6, 7. Well, these two guys start talking. Hey, I got 1. I'm no good. That's okay. I got 7. I'm no good. Maybe we could be good together. Aw, isn't that sweet? So this electron says, hey, I'll come over here. I'll come right there. So that one goes here. So what we end up doing is we lose this electron. So we will erase this. That's gone. So the electron came here. This one lost one. So if you lose an electron, that becomes more positive. This one gained an electron, so that becomes more negative. That's an ionic bond. So we have something called Na plus Cl minus, plus minus, sodium chloride. The electron was donated here. The chlorine accepted it. So this becomes the positive. This one becomes more negative. Okay? So I left the slide here for you to take the time. You don't have to do it now, but you could draw that out, right? Once you know the protons, you know the number of electrons, you just start plugging them in. Remember the rules. 2 go in the first shell, 8 have to be in a second. If it needs to add a third, fine, but there also has to be 8 in that outer shell. Otherwise, it's unstable. So that's an ionic bond. That's a give and take type of relationship. But covalent bonds, these are different. We're not losing, we're not gaining. What we're doing here is we're sharing. I only got 1 apple. We can share it together. Sharing is caring. So when we look at hydrogen, hydrogen has 1 proton. Is that stable or unstable? Well, that's unstable because we know that the first electron shell must have 2, but there's only 1. But if we take this hydrogen and this hydrogen and put it together, now we have a molecule. A molecule is when we bring 2 of the same together. There's an oxygen molecule, 2 of them together, and a nitrogen molecule, 2 of the same. But in that first shell, it looks and appears like there's 2 on this side. It looks and appears like there's 2 here. Oxygen does the same thing because in the outer shell, there's only 1, 2, 3, 4, 5, 6. If we bring them both together, 2 oxygen atoms combined, we count them. You got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Stable. That's O2. This is H2. Nitrogen, you got 2 in the first ring. That's stable. How many do we have in the outer ring? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If we bring these together, you see these share, you end up getting 1, 2, 3, 4, 5, 6, 7, 8. Stable. 1, 2, 3, 4, 5, 6, 7, 8. Stable. And 2. So the difference between ionic bonds is that there's a losing and gaining in this type of relationship. There's a sacrifice made, gaining or losing. In covalent bonds, we're sharing. We come together and hold hands. That's covalent bonds. Here's another example where, in this case, in here, we brought the same, 2 hydrogens, 2 oxygens, 2 nitrogens. But it doesn't always have to be that. Here we have carbon, and you see that there's 1, 2 in the first shell, 1, 2, 3, 4 in the second. That's unstable. We need 8. But how many did hydrogen have? Hydrogen had 1 proton, 1 electron. So we can take one of these, hook up here, one of these, hook up here. This one can hook up here, and this one can hook up here, so that you have this hydrogen bonding to that other electron on carbon. And what you end up with is a central carbon bonded to 4 hydrogens. C, 1, 2, 3, 4. C, there's 1, 4 hydrogens. CH4, that's methane. And in the human body, this is super important for a process called methylation. A lot of people, if you may have heard, they go for genetic testing for MTHFR, which stands for methylene tetrahydrofolate reductase. This is an enzyme. When people don't have this enzyme, they have trouble methylating. And methylation requires 3 B vitamins also to happen, B6, B9, and B12, in order for that to happen. Methylation is needed for DNA synthesis, RNA synthesis. It's needed for your neural system to develop, for a healthy brain and spinal cord and neurotransmitters. You have to methylate. Methylation is required to make thyroid hormones. Methylation is required for weight loss. So a lot of people go, whoa, you know, I have migraine headaches. I'm having difficulty losing weight. I have a child with ADHD. I have a child with autism. I need to check MTHFR. So they'll go for a genetic test. 2 of them. One is called the C677T, and the other is called the A1298C. These are 2 methylation tests that check the ability of your body to produce methyl tetrahydrofolate reductase, the enzyme that's needed. Okay. Here we have H2O. Again, we have oxygen that only has 6 electrons in the outer shell, 6, and we know hydrogen has 1 electron. So if we take this one and go here, pair that one up, go here, we pair that one up. Now you have 8, and you have something stable called H2O, 2 hydrogens, 1 oxygen. Okay, so this ends up creating what's called a hydrogen bond between hydrogen and water. It's a weak bond. They're constantly made and broken, made and broken. We know that water can be a liquid, it could be a solid, it could be a gas, because these bonds are easily broken, those hydrogen bonds. So here's an example again, the hydrogen bonds. It results from an attraction of, what do you know, oppositely charged particles. So we have negatives and positives. Positives and negatives are drawn, so we end up with these hydrogen bonds. Okay, but these bonds can be made and broken pretty easily. Hydrogen bonds between water molecules give water cohesion. Cohesion is the tendency of like particles to stay together. Okay, Hydrogen bonds also create surface tension. Like you ever see an insect walk on water, or a spider on the top of a pool on the water, or an insect that maybe hits your eyeball and then just bounces out and bounces off of it due to that surface tension. So the hydrogen bond is what creates the surface tension, but it also creates cohesion, right? Think of if you take a slide, like a microscope slide, it has that little circle on there, and you put a drop of water, a water droplet right there. And then you take a plastic shield like this, and you place it right on top of it, and you press it down firmly. Could you easily could you easily dig your nail under here and peel off that other plastic layer on top? There's cohesion, it sticks. The only way that maybe you can slide that off is perhaps if you put a slippery, maybe a little bit of soap under there. Now it becomes slippery and you can manipulate it and slide it off. Good place to end this. We'll take a break. When we come back, we'll get into chemical reactions.